All right, now moving on to reaction rates. Exactly how do we measure the rates of reaction, or how fast reactions happen? So if we take a look at a reaction, remember that rates, and those who are in physics, rates are always something, changes in something over time. So if we take a look at a chemical reaction, just simple A going to B, we have a certain number of A molecules at the start, and then as the reaction progresses, the amount of A goes down, the amount of B goes up. So we could look at the rate of this reaction either in terms of the decrease in number of moles of A or in the increase in number of moles of B. Now typically what we do is we look at changes in concentration. Concentration is something we can measure in the lab in a variety of different ways. So if we take a look at this reaction, then, for instance, we might measure the rate of this reaction as the change in the concentration of A over the change in time. Okay, so we'll take a look at a couple of examples of this. So here's a reaction of butyl chloride reacting with water, forming butanol. And you can see that in the table here, there's a listing of the concentrations versus time. And so to figure out the rate of this, change in concentration over change in time, we can imagine taking each of these, and we'll do this in just a moment, finding the difference in the concentration and dividing by the difference in time. So if we take a look at that, so let's just put a little equation how we figure out the average rate. Now it's the average rate because it obviously doesn't stay the same. If you look at the rate changes, we're starting at 1.9 times 10 to the minus 4th molarity per second, and that change keeps getting smaller, that rate of change. So the rate of this reaction does get slower as it goes on. Why do you suppose that happens? That rate of reaction goes down as the reaction progresses. So again, the way we determined this was rate equals the change in concentration, in this case the butyl chloride, divided by the change in time. And so that's how we got those values. Now if we take the concentration in time and we plot that, we get a graph that looks something like this. And notice again that rate decreases. So if you take a look at the slope anywhere along this line, which is the change in the concentration over change in time would be the slope. If you found the value of that slope at any particular point, you would find the instantaneous rate at that point. So again, as you can see from this reaction, that slope then decreases, which means the rate of the reaction decreases over time. One of the things that we'll do when we start doing experiments with this and getting experimental data, the best indication of a rate of a reaction is the instantaneous rate right at the beginning. All right, we oftentimes call that the initial rate, or the rate at time t equals 0. Okay, so again, our average rate is given down here. Now you notice that in this equation I've got a negative here. Rates of reactions have to be positive. So if we're looking at the change in concentration of a reactant, obviously that's going down. Change is always final minus the initial. So that would give us if we looked at the change, it would give us a negative value. So to make the rate positive, we would have to add a negative sign to the front of that. We could have also looked at the change in concentration of one of the products. Now in this case, if we looked at the butyl alcohol, the butyl alcohol will change at the same rate as the butyl chloride because there's a 1-to-1 ratio. But what happens in a reaction where the stoichiometry isn't 1-to-1? Well, if we look at this reaction here, we note that for every 2 molecules of hydrogen iodide, you're forming 1 molecule of iodine, I2. So if we wanted to write the rate equation for this reaction, either in terms of the reactants or the products, we would simply take into account the stoichiometry of the reaction. So we would, by convention, use the coefficient in the equation to, kind of alter the magnitude of that rate. So, for instance, the hydrogen iodide, we would use a negative in front because it's a reactant, and then 1/2. So it's 1/2, which is the coefficient from the iodide or the hydrogen iodide, and the iodine would just be the change in the concentration. Again, this is because the iodine concentration is going to change half as fast as the hydrogen iodide, or the hydrogen iodide concentration would change twice as fast as the iodine. Looking below here, we have then a general formula for this, that if you have a generic formula here for reaction AA plus BB going to CC plus CD, the rate of the reaction, and a little bit off the chart here, the rate of the action would be equal to negative 1/A times the change in concentration of A over time, change in time, and et cetera on for the other ones. Again, keep in mind that the negatives are for the reactants because their concentrations are going to decrease over time, whereas the products' concentrations will increase.